it was fine. It was fine.
I needed somebody to tease.
No, I know. I kind of felt like I was back in Chicago now, but yeah, so I also I tried to like
Amos Nevo from Technion. He's going to talk about Ergodic Theorems for lattice sections on homogeneous spaces and some applications.
I'd like to thank the organizers very much for the opportunity to give this talk. I was always, of course, very interested and very impressed by the very large collection of ergodic theorems and equidistribution results proved by Ratner, and the many applications that it had to various aspects in number theory and Diophantine approximation, which was developed by many people over a long time now. But on the other hand, I was sort of watching all of this from a safe distance. And what I would like to do today is to present some results on ergodic theorems, which have a completely different flavor. I think maybe borrowing from Alex's talk in the morning, the ergodic theorems I'm going to talk about, they're based on analytic methods rather than on dynamics, primarily of unipotent flows. And I have two goals in this talk. One is that I would like to present one case in which both of these approaches sort of combine to give a very interesting problem, which is perhaps very difficult, but it's quite striking. And the other thing I would like to do is to present a large collection of applications which are very natural for these ergodic theorems, but perhaps are not so accessible using equidistribution results along those that arise from Ratner's theory. So the plan of the talk is as follows. We are going to talk about effective ergodic theorems for algebraic groups to begin with. This is older results. And then we're going to talk about ergodic theorem for lattice subgroups. And then we're going to talk about the problem I briefly mentioned, which has to do with minimality, unique stationarity, and effective genericity, which I will explain. And finally, I would like to talk about actions of lattice subgroups on homogeneous spaces and some of their applications. And the most striking of those is probably to intrinsic Diophantine approximation. And if we have time, then I'll say a few words about how this is based on, how this approach is based on effective duality principle in homogeneous dynamics. Okay, so let's formulate things without any distinction between real and p-adic groups. So let G be a locally compact second countable unimodular group with Haar measure Mg. And Bt, a growing family of Borel sets of positive finite measure. X mu is an ergodic probability measure preserving action of G. And we consider the Haar uniform averages beta t supported on Bt. So pi x pi beta t f x minus the integral. I'm sorry. Pi x beta t f x is the average of f along the orbit, the values of f along the orbit of G, taken with the uniform measure on Bt. And these are, of course, also known as the time averages along the orbits. Okay, so these are the basic elements of ergodic theory, you might say. And the first result I'd like to mention is an effective mean ergodic theorem. And it has the following formulation. For any weak mixing action of a simple algebraic group, G, which has a spectral gap, and for any family Bt in G such that the measure of Bt converges to infinity, the convergence of the time averages pi x beta t to the space average takes place at a definite rate. And that definite rate is a negative power of the volume. And here theta is any number strictly less than a certain crucial parameter theta x, where the main point, of course, is that this is positive. And theta x is a measure of the spectral gap of the action. And if G has Kazhdan's property T, then theta x is in fact independent of x, and it can be stated explicitly. In other cases, when G doesn't have property T, it can often be estimated. You are spoiling the, the play has several sets. It's, but to your question, this is an L2 statement. Okay.
That was the part of this, that was the non-question part.
Okay. Okay, so I'm going to say this very briefly because I don't want to get into any technicalities, but a similar result holds for any semi-simple S algebraic group. But there are a number of technical issues that I really do not want to discuss. I don't think that's the main point here. I'm just going to say briefly that we have to replace the spectral gap by a strong spectral gap, whatever it is. We have to assume that the sets Bt are balanced among the various possible simple factors. And we have to restrict the action to the group G plus generated by unipotents, or otherwise assume that the action is weak mixing. Okay, but the statement, I think, for a simple group is very clear. And now I'd like to say, to make a few comments about this result. So looking again, say, at the case where G is simple and connected, we note that the only requirements that the set must obey is that the measure goes to infinity. And no aspects of their geometry or their level of regularity affects the final result. And that is a very striking fact, which is really not classical. I mean, this is not what you would expect in the case, well, the classical case of ergodic theory of a billion groups. If you think about the plane, well, it's just not true that every every increasing family of sets that you will place in the plane will have an ergodic theorem like that. And this fact allows for a great deal of flexibility in the applications of the effective mean ergodic theorem. Okay, so the result is a consequence of certain estimates in the unitary representation theory of simple algebraic groups, together with a very important convolution theorem which originates already back in 1960 in the work of Kunze and Stein. Okay, but so as I said, these are analytic methods, but I'm not going to say much more about them. And I will only say that one such application of the mean ergodic theorem asserts that under natural additional regularity assumptions on Bt, for example, that they are Lipschitz or Holder well-rounded, the effective mean ergodic theorem implies a general effective solution of the lattice point counting problem in the domains Bt in G. And again, the sets would be fairly general. They definitely have to be regular now, because otherwise the lattice point counting problem doesn't even make sense. But it is still quite flexible. And again, similar comments apply in the case of semi-simple S-algebraic and Adel groups with some sort of caveats. But the quality of the error estimate that the effective mean ergodic theorem provides is the best currently known for irreducible lattices in higher rank semi-simple group other than powers of SON1. In the case of powers of SON1, one can adapt some methods of Selberg and later on Lax and Phillips and prove a result which has a somewhat sharper estimate. But the real rank 1 and the products of real rank 1 are very special, and nothing like that is known in higher rank. Okay, so this result generalizes and sharpens some counting results by Duke, Rudnick, and Sarnak a long time ago. Eskin, McMullen, Benoit, and O, and Gorodnik, Mokora, and O, in the case of Adel groups. Now, we're going to talk about the considerably more challenging problem of pointwise convergence. And here, stronger stability and regularity assumptions on the sets BT are required. And for simplicity, again, we will formulate them only for real groups. And so we assume that G is a connected Lie group with finite center, and we fix any left invariant Riemannian metric on G, and consider the corresponding small neighborhoods of a point of the origin. And an increasing sequence of compact sets BT of G will be called admissible if there is a positive constant C such that for all t sufficiently large and epsilon sufficiently small, we have this stability property that the sets have this sort of near stability under small perturbations on both sides, and that the volume of the sets obeys this estimate. This is just saying that the log of the volume is a Lipschitz function. Okay, and so under this assumption, we can prove, answering your question, an effective pointwise theorem. So let G be a connected simple Lie group with finite center and BT admissible, and assume that the G action has a spectral gap. Then for some fixed theta x, which depends on P, and for F in LP, and here P is strictly greater than 1, and we have that for almost every x, the time averages minus the space average converge to 0 at a definite rate. And again, provided that theta is less than this crucial exponent, theta xp, which depends on P. And as before, theta xp depends on the spectral gap, and if G has Kazhdan's property T, it is independent of X and explicit. And the estimator, CXF, is finite almost everywhere. Well, that's the content of this theorem, but in fact, it has a finite LR norm bound, where R is a complicated function of all the other parameters here. But this is not some arbitrary estimator. It has good analytic properties. Yes.
Somehow, when you state these theorems, you think of a one-parameter family of following sets. But in the statement, it seems that you're saying something for any set of BQ sets. I mean,
If it's admissible.
making a one-parameter family and not just a statement about sets, about averaging your function.
I can't in this particular case. In the case of the mean, this case is very different. Yeah.
So, is this the conceptual thing? To think of what
It's not just a conceptual thing. I mean, in fact, that Lipschitz property that I mentioned, these averages at some point are going to get differentiated in a certain function space with respect to t, etc.
somehow in the constant there, which depends on f and on x, also the amount of some of the regularity of the family.
The constant, sorry?
T doesn't play a role here, right? What is little t in this inequality?
In which inequality? In this inequality? It doesn't play a role? I don't understand what you're saying.
It's just an integration over a set B.
T.
Static statement, right? T doesn't need to go to infinity.
What do we ask if T enters the only Pt? Does it enter in CFX?
Sorry?
The constant family B enter also in CFX?
The family B is what? Sorry?
Go ahead. Go ahead. I will back you up.
Okay. Yeah. Well, I mean, since we are talking about regularity, then I will say this is that the admissibility condition is absolutely crucial, and it's considerably stronger than Lipschitz well-roundedness. It gives rise to the possibility of certain differentiation along the parameter t, and this differentiation process is actually crucial in obtaining certain analytic estimates associated with square functions and analytic interpolation. So the assumptions are actually quite, I mean, admissible families are much more stringent, obey much more stringent requirement than well-rounded families. Okay, so so as before, similar results holds for semi-simple S-algebraic groups. Okay, so now, having said all that, we would like to pass on to averages on lattice subgroups. That's a completely different issue in some sense. So, but again, let's start with G, a connected simple Lie group with finite center. And gamma here is going to be a lattice subgroup, and BT an admissible family. And let lambda t denote the uniform measure on the finite set of lattice points. Gamma intersect BT, which we denote by gamma t. So if gamma acts on x mu preserving a probability measure mu, then the averaging operators associated to lambda t are going to be now pi x lambda t. It's the average on this set of lattice points. It's the average on this set of lattice points. Again, as usual in ergodic theory, we average on the orbit of x with elements gamma in gamma t. And maybe actually it would be good to say that good examples of such admissible sets BT arise, for example, when we take essentially the Riemannian balls in symmetric space, Riemannian balls of radius t in symmetric space, or if we take certain norms in linear representations, etc. So this is averaging a function gamma, a function f on the elements of gamma in a norm ball. This is a good way to think about it, or in a Riemannian ball. So under these assumptions, we have an ergodic theorem for lattice subgroups. And here, so here the first thing we can say is that for an arbitrary ergodic gamma action on a probability space, the mean ergodic theorem holds, namely for every p at least 1, the norm of the average lambda tf minus the space average converge to 0. So I'm going to say two things about this. One, is that the point here is that the action is completely arbitrary. And gamma has many, many, many more actions than G does. Gamma could have actions which are isometric on a compact space, which G definitely does. Gamma can have actions on finite spaces, which G definitely does not. Gamma has, I don't know, an action on the profinite completion. Gamma has a lot of actions which have nothing to do with G. But the statement here is for an arbitrary action. It's not a restriction of an action of G. And the second thing that I would say that in this generality, even the mean ergodic theorem there aren't a lot of precedents for it. Of course, a gamma, a lattice can have actions with and without a spectral gap, unless, of course, it has property T itself. And in the case of And apart from the mean theorem, we have the pointwise almost sure theorem in this case. Notice that there is an important difference, which is that P now has to be strictly greater than 1. This is a very complicated set of issues which I'm not going to get into. There was some progress on these issues recently, but I'm not going to get into that. And again, this result holds for all gamma actions. And the only connection to the original embedding of gamma in the group is in the definitions of the sets gamma T. This means that there is a lot of sets like that, gamma T in gamma, because there could be several embeddings, or there could be different embeddings. You can even conjugate. And there are many admissible families on G. Okay, so now let's consider the effective ergodic theorem for lattice subgroups. And so here again, under the previous assumptions, let's say if the gamma action has a spectral gap, then the effective mean ergodic theorem holds so that the time averages converge to the space average at a certain definite rate. The measure of BT to some power theta prime P. I'm writing theta prime to distinguish it from the theta that was valid for G. This is a separate parameter. And okay, so theta P has to be smaller than a certain critical parameter theta prime X. And under this condition, the effective pointwise ergodic theorem holds. For every f in LP, P greater than 1, and for almost every x, the time averages converge to the space average at a certain rate, almost surely. Okay, and as above, similar results holds for lattices in S algebraic groups, but again, you have to make the formulation considerably more elaborate. Okay, so it's probably not going to come as a big surprise to say that the first thing we're going to do to approach these theorems is to induce the gamma action to G. Now, we are going to get this way a certain G action on a probability, ergodic G action on a probability space, and there's going to be an elaborate analysis which reduces the ergodic theorems, the pointwise, effective, whatever ergodic theorem for BT on G to ergodic theorems for BT intersect gamma on gamma. So this is a certain, this is a certain analysis. It's quite elaborate, but that's really the way this result progresses. And now I'd like to note that there is a very interesting problem here that arises when one compares or one combines this result in a space in which some of the results proved in Ratner's theory apply. So assume now that G or gamma act continuously on a compact metric space. And assume that mu is an ergodic invariant probability measure for G or gamma of full support. And assume, furthermore, that mu is the unique stationary measure for the action of G or gamma on X. And so, in particular, it is the unique invariant probability measure. And then the action is then also minimal. This is a consequence of unique stationarity, but not a consequence of unique ergodicity. And finally, assume that G or gamma action on X has a spectral gap in L2. This is a long list of assumptions, and these spaces would be quite remarkable. Yes? You use essentially any, I mean, did I say G is connected? But okay, essentially any, well, I don't know, a probability, the uniform probability measure on a ball of radius 1, let's say. Yeah. And it is one of the remarkable consequences of Ratner's theory and its extensions that these stiff, uniquely stationary actions with a spectral gap are actually quite common and give rise to many interesting examples, and I'm going to mention a few just now. So this concept of stiff actions was introduced by Furstenberg, but these stiff actions are really also, well, we have an additional list of requirements for them. And so consider homogeneous dynamics and let H be SL3R. And let lambda be a uniform lattice in H. And let G be SL2 in the upper left-hand corner. And so then H mod lambda is a compact space on which G acts. And when the action of G on H mod lambda is minimal, then the G action has these stated properties. And such a result in much greater generality follows from Ratner's measure classification theorem, together with work of Dani and Margulis and Moses and Shah on invariant measures, in the case of invariant measures, and Eskin, Margulis, and Benoit Kant in the case of stationary measures. So the production of this example is actually really very impressive. Also, maybe I should mention that one also has to argue that SL2R has a spectral gap in this action. That's a feature of unitary representation theory. Maybe this is not as hard, but all of these ingredients come into the picture to produce these examples, but these examples are actually quite robust. It can happen in Ratner's theory quite often that a semi-simple subgroup will be minimal and uniquely stationary on H mod lambda. Now, another very interesting collection of examples, and here I'm going to borrow heavily from Barak's talks on H11 and Alex's talk this morning. So here G is going to be SL2R, and it's going to act on the strata H11 of translation surfaces. In this space, which is not compact, the G invariant ergodic probability measures were completely classified by McMullen. And there exist certain invariant non-compact subsets, epsilon D for certain D, each of which support such a measure, which were described by McMullen. This measure is of course singular with respect to the invariant measure, the invariant volume measure on H11. And this measure is uniquely stationary by work of Eskin, Mirzakhani, and Mohammadi that Barak mentioned. And the spectral gap, which is also very challenging in this case, is due to the work of Avila, Gozel, and Yokos. So here again, these examples really exist, and again, they may appear, maybe they're not so rare, but there's really an enormous amount of very, very difficult results that are used to prove their existence. And so the question I would like to ask is about, is natural when you combine both of these points of view. So what about fast everywhere convergence? And so in the first case, in homogeneous dynamics, it was established by Gorodnik and Barak-Weiss using results of Shah, of Nimi Shah, that for Bt defined by a norm on G equals SL2R, the corresponding averages pi x beta t do in fact converge to the integral for every x in X f and for every continuous f. This is included in a certain important paper that Gorodnik and Barak-Weiss wrote in 2007, in which they leveraged work along Ratner's theory, contributed to by several people, particularly by Nimi Shah, to prove this equidistribution result. And in the second case, Eskin, Mirzakhani, and Muhammadi showed that every point on those sets ED is generic. But generic here means that generic with respect to a family of averages which are very different than our beta t that we focus on here. And we don't know whether, in fact, every point is generic under averaging over balls in SL2R. As far as I know, in this case, yes. For unipotents.
This is my sense from my first lecture. I said that this kind of polynomial divergence applies to essentially homogeneous spaces. Is one exception, and I forgot to mention the exception. This is the exception. It actually works here. So like in Barak's talk, there was a set E, which is really one of them. And so all of this pathology about stuff doesn't happen as long as you stick inside it. As soon as you move away from me, you see all this pathology. But inside these sets, you have to have polynomial divergence.
Equidistribution for n. Yes. Still, still I'm asking for beta t.
No, it's for spheres also.
For spheres. Okay. But the question I really want to ask is whether one would have effective equidistribution. So here's the question or the problem. So let S mu be stiff, uniquely stationary, ergodic action of G. G can be SL2 here, of course, with a spectral gap. So is it true that every point is effectively generic under beta t, so that the usual statement holds, and we have a certain rate of a certain rate of convergence, maybe a rate of convergence depending on x, and that for every Lipschitz functions f on x. And the same question can be asked, does this hold with gamma and lambda t replacing g and beta t? And the point here is, one of the motivating points here is that, in fact, the effective pointwise ergodic theorem implies that this is true for almost every x, with kappa x greater or equal than that parameter theta x. But when the action is uniquely stationary, that is probably the case where you are entitled to ask whether this reflects on every single point. So as far as I know, this has not been established. This would be a very striking dynamical system with a very interesting property. So yeah, okay. So this is the problem I wanted to present about combining the construction of these spaces with unique invariant measure and unique stationary measure, and effective estimates which are only true almost surely. Now, one thing I would like to mention is that maybe one would sort of wonder whether this phenomenon can actually exist at all. And I would like to make the point that it does, but not, I don't know any example like this for G, but we can consider equidistribution in isometric action. And of course, G does not have any isometric action on a compact space. And so here we can state the following. So let SD be a compact metric space, and gamma act by isometries ergodically with respect to an invariant probability measure mu of full support. And assume that lambda t satisfies the mean ergodic theorem. And then for every continuous function f, we have uniform convergence of lambda t to the integral. So in particular, convergence holds for every starting point. This is a very, very, so this is based on a very, very elegant argument which was initiated by Givarch in his work on free groups in 1968. And if the gamma action has a spectral gap and gamma satisfies the effective pointwise ergodic theorem, and the measure satisfies that the measure of a small epsilon ball in S of radius epsilon is at least C epsilon to some power K, then for every Helder continuous function f and for every point x, the averages lambda t minus the space average do in fact converge. I wrote it here, e to the minus kappa t, or this, well, okay, e to the minus kappa t, with kappa positive depending on the Holder parameter of f and the spectral gap, but not on f and x. And that result is really not very difficult. It's in the isometric case, well, I mean, there's no need to tell everybody that the isometric case is much easier to handle than any other ergodic situation, and this result is really quite straightforward. Once you have almost sure effective pointwise ergodic theorem in the isometric case, it's not so difficult to handle it. But of course, the examples we had before were not isometric. Okay, so I said that I would like to explain some of the applications of these results, and I'm going to start with applications of isometric actions. So, for example, this applies to the action on any profinite completion, including the congruence completion in the case of arithmetic lattices. This is with respect to Haar measure on the compact group. And if your lattice gamma has a representation in the unitary group, which has dense image, then for every unit vector, the set sigma gamma tu become equidistributed in the unit sphere with respect to the rotation invariant measure. Since here the dimension is finite, when the action has a spectral gap, then theorem E part 2 applies, and it gives a rate of equidistribution at every single point of the sphere. This generalizes the effective equidistribution part of the Lubotsky-Phillips-Sarnak theorem, which was for certain dense subgroups of SU2C. And this was followed later by the results of Clausel, O, and Ullmann to all lattices in simple group with property T, for example. So again, if you have a lattice with property T, and these lattices can have a lot of dense embeddings in SUN for various n's. Then you take that lattice, you view it as a lattice in your simple Lie group. Then you take Riemannian balls or norms. You look at all the elements of the lattice gamma of a certain norm. And then this is a good average on the sphere. This is an efficient average on the sphere. This average, as t goes to infinity, will converge to the average of the spheres exponentially fast for every initial vector. So in the work of Lobotsky, Phillips, and Sarnak, there were some specific averages like that for certain dense subgroups of SU2C, but they pointed out to a very, very interesting question, of course. And, okay. So another thing I would like to say is the effective mean ergodic theorem applies in particular for every action of gamma on a finite homogeneous space. This may look ridiculous, but let me dwell on it for a moment. It yields the following norm bound for the averaging operators. Now, in the finite case, this is the only interesting part. So this is pi x lambda t, in this case, is a certain finite matrix. But it's a finite matrix which depends on t. And so we have a non-trivial estimate on the norm of this finite matrix minus this projection. And this theta really depends only on the spectral gap for the induced G action. And so, for example, if gamma is a lattice satisfying property T or property tau, the estimate goes well beyond the basic estimate which is guaranteed by property T for gamma itself. That estimate is only asserting that this norm is less than 1. Okay, so let me make a remark about this. So property T, it guarantees only separation from the trivial representation, and it has no bearing at all on norm estimates. Well, okay, other than saying that the norm is less than 1. In dynamics, of course, what you would really like is to average on a ball of radius 1, and then average on a ball of radius 2, and then average on a ball of radius t, and you would like the norm to decay. I mean, this is an obvious statement, but property T has simply no bearing on this problem. This is an analytic challenge, even to show that this norm goes to 0, actually, and certainly to show that it goes to 0 like a power of the volume. And so this estimate, even in finite spaces, even in finite dimensional representation, has content. And this uniform norm estimate can be used, let's say in the case of property T, to establish deterministic sifting results in a large norm ball. This is our context, that large norm balls have decaying norm. And this can be used to establish deterministic sifting results in a large norm ball, motivated by the work of Kowalski and his collaborators, and also Lubotsky-Meiri. They, of course, considered only the case of random products. And the reason they did this was that, indeed, for any probability measure on the group, pi x of that probability measure minus, well, the measure supported on the generators have his norm strictly less than 1. Of course, that immediately implies that the norm of the convolution powers decay exponentially. But what we have here is a different statement, which is unrelated and independent. We're talking not about the norm of the convolution powers, but the norms of the uniform measure on a norm ball. And so, if you have exponential decay for that, you can attempt these sifting problems, but not for a random product, but for elements in a large norm ball. So, for example, it can be shown that the characteristic polynomial of every integral unimodular matrix gamma in SLN Z in a large norm ball has Galois group the full symmetric group, with a set of exceptions being of strictly lower order of growth. So this is an analog of these sifting results where you replace with high probability by for all elements in a large norm ball except with a power saving, except a set of exceptions which has lesser growth. So this is just to say that even norm estimates in a finite representation have their utility. And now I would like to pass to the main application that I want to show, which is lattice actions on homogeneous spaces. And so let's set up the problem first. So let G be a locally compact second countable group, and let gamma be a discrete lattice subgroup of G. Let H be a closed subgroup of G, and assume either that every orbit of gamma on G mod H is dense. This certainly happens sometimes. Or, more generally, that gamma is ergodic on the unique gamma invariant measure class on G mod H, and in that case, at least almost every gamma orbit is going to be dense. Both cases, well, okay, I mean, both cases arise very in great abundance. And now let the norm of G denote a norm. This, in this generality, just simply means a gauge on G, namely a continuous non-negative and proper function from G to the non-negative reals. And let D denote a metric on G mod H inducing the topology, and we would like to analyze the efficiency of approximation of gamma orbits on the homogeneous space G mod H as follows. We let X be in G mod H and suppose that for sufficiently small epsilon, for every X naught in GH, we can solve the inequality that states that we can take X by an element of gamma close to X naught. And with gamma, in gamma satisfying a norm bound. The norm is bounded by 1 over epsilon to the zeta. And here zeta in principle is a function of the two variables x and x naught, and of course gamma, g, and h. Yes? Sorry? Exactly. Definitely. Therefore, zeta x naught gives a rate of approximation of a general point x naught in GH by the gamma orbit of x, which, of course, we assume is dense. Okay, so now here is a crucial point in this talk. So note that the problem that we state here amounts to establishing properties of gamma in gamma lying in a large norm ball. That is the issue here. I mean, of course, many other questions can be asked, but it's very natural from this point of view. We are really interested in the behavior of elements in a lattice in a large norm ball. Okay. And so let kappa xx naught be the infimum of these admissible rates. And the basic problems, and so what I'm going to describe now, to the extent that I will have time to do it, I would try to describe, and this is going to be sort of quite impressionistic except for two examples, a general approach to this problem. And the general approach is going to be based on these ergodic theorems. So what would we like to do? The first problem would be to establish finiteness, namely to determine when does there exist a finite constant kappa gamma gh which bounds the rate of approximation by almost every lattice orbits. And more ambitiously, we would like to determine when does there exist a finite uniform bound for every single lattice point without exceptions. Okay, well, for that we would certainly have to have every orbit be dense. And another thing that is quite interesting and arises in a number of applications is to establish explicit bounds, namely an upper bound and a lower bound for the rate of approximation, and we would like to explicate their dependence on G and H and gamma explicitly. And a challenging, very challenging problem is to try to establish optimality. So to give a criterion which hopefully is simple and widely applicable for when the upper and lower bounds coincide, giving rise to optimal rate of approximation by lattice orbits on the homogeneous space. Now, I'm going to spend 2 or 3 minutes describing briefly that this is really a very large problem, and it has a lot of instances. So we can start by approximation by the lattice of integer points, a very familiar object that we have been discussing pretty much in every talk. For example, GR is a real algebraic group defined over Q, HR an algebraic subgroup, gamma equals GZ, the lattice of integral points, and this includes natural Diophantine approximation problems on homogeneous affine varieties and homogeneous projective varieties. We can consider approximation by any lattice because there is no arithmeticity in this problem. So G is any connected Lie group, let's say, and H is a closed subgroup, and gamma is a not necessarily arithmetic lattice. This includes the case, for example, of H being a lattice subgroup itself, and in particular lattice orbits approximation on finite volume locally symmetric spaces. We can consider by approximation by rational points with constrained denominator. So G is an S algebraic Q group and H a closed subgroup. Gamma is the S arithmetic lattice. And for example, this includes the case where G, the group G, is a product, GR times GQP, and H is GQP. And so G mod H is just the group GR. And so this amounts to approximation in the connected group GR by the dense subgroup GZ1 over P. Let me make this a little bit more explicit. You can consider the group SL2R, which you think about for a moment as an analog of the real line. And you can consider a dense subgroup of SL2R, for example, all the SL2 matrices with values in the ring Z1 over P. You can consider the dense subgroup SL2Z square root of 2, countable dense subgroup consisting of all 2 by 2 matrices with values in the ring Z square root of 2. You can go ahead and consider the dense subgroup SL2Q consisting of all rational matrices. These are all, so it's a very legitimate problem to try to analyze the efficiency of approximation of a 2 by 2 matrix, real matrix, by these algebraic or rational elements. And that problem is really completely analogous to the classical case of Diophantine approximation on abelian, on vector groups. But all of these problems I would like to think about as belonging to this case. In other words, it's the action of a certain lattice subgroup on a homogeneous space. In this case, the homogeneous space is GR times GQP modulo GQP, which gives you GR. So, as I already said, we can also approximate by all rational points. We take G and H to be groups of rational adels and gamma the lattice of rational points. this case includes the Diophantine approximation by the set of all rational points lying on the algebraic variety, GR over HR itself. Yes. Okay. Now, in fact, this is very okay. So this problem has a very large scope, and of course, if you want to make it even larger, you can consider arbitrary locally compact fields and arbitrary lattices. And a very important point, which, well, I don't know if I'll be able to get back to it later, is to consider not only establishing the Diophantine exponent, but also much finer results in Diophantine approximations, such as Khinchin's theorem and other refinements like the Schmidt solution counting theorem, etc. Okay, how much time do I have? Because I was supposed to finish two minutes ago. 5 more minutes. Okay. So I would like to mention that, okay, so establishing properties of Diophantine approximation for a general real point on a homogeneous variety defined over Q by rational points on the variety itself, we will refer to as the problem of intrinsic Diophantine approximation. We are only allowed to use rational points on the variety itself, and not in the some ambient vector space. And it turns out that this problem was actually raised explicitly by Serge Lang in 1965. And one can certainly say with great, with a lot of evidence, well, one can definitely say with great confidence that it hasn't received a lot of attention. And except for the case of commutative algebraic groups, there's been essentially no progress on it until 2011. But the ergodic theorems that we stated above are instrumental in developing a general approach to establishing explicit bounds for Diophantine exponents on a large class of homogeneous algebraic varieties, and it gives sufficient conditions for optimality also. And this approach was initiated in 2011 jointly with Ghosh and Gorodnik, and is still going on. Maybe for a very long time, because this is really quite a large problem, but certainly some progress has been made. So what I'm going to do in my last 2 minutes, instead of trying to talk about more generalities, I'm going to give just two very, very elementary explicit examples. So let's consider the linear action of SL2 on R2. And here, Loren and Noguera established that generically the Diophantine approximation exponent K XX naught is less than or equal to 3 for the specific lattice gamma equals SL2 acting linearly on the plane. And they did this by explicit construction of a sequence of approximant via the continued fraction algorithm. Conjecturally, the general exponent is equal to 2. Now, I think it's hard to find problems which are more elementary, which are formulated more elementary. We have SL2Z, it acts on the plane. Almost every orbit is dense. This is well known, of course. And so the question is whether there is a bound on the efficiency of approximation for almost every orbit. And the conjecture is that this bound is 2, and they have proved that this bound is less than or equal than 3. Mokorant and Barak-Weiss established an explicit but not as sharp upper bound for arbitrary lattices. And that was actually using results on the effective equidistribution of horocycle flows. For co-compact lattices acting in a complex plane, such bounds follow from effective equidistribution results of Polycott. So, for the linear action, determining the exact exponent remains an open problem for any lattice subgroup over any field in any dimension. So it's a very simply formulated problem, but it's completely open. And it's possible to give explicit upper and lower bounds, which we have established in this joint work in 2011. However, let's move from the affine action, from the linear action of the plane to the affine action of the plane. S gamma now is going to be SL2Z, semi-direct product Z2. And now it is possible to establish the optimal rate, and the optimal rate is kappa equals 1. More precisely, for every vector u0, comma v0 in R2, and almost every uv in R2, and for every epsilon sufficiently small, it is possible to solve gamma inverse x minus x0 less than epsilon with the norm of the matrix bounded by b over epsilon times log 1 over epsilon cubed. For example, this has the following implication in planar inhomogeneous Diophantine approximation. If we take the resulting two inhomogeneous equations mod 1, we conclude that for under the same conditions, for almost every vector uv in the two torus and for every epsilon sufficiently small, there are integers a, b, c, d such that au minus bv, comma cu minus dv is close to u0, v0 up to epsilon, such that the maximum of a, b, c, d is less than b over epsilon log 1 over epsilon. Well, this is just the second statement is the first statement modulo z. Now, what is the big difference? This is going to be my last comment. What is the big difference between these two cases? Well, the plane is SL2R. The plane is SL2R modulo n, the unipotent group. Essentially, that is the plane minus the origin. But we can also look at the plane as the homogeneous space SL2R semi-direct R2 modulo SL2. And so it's G mod H, and the big difference here is that H is simple, not unipotent. And now one applies a certain philosophy for which many people here are responsible, namely the philosophy or the principle of duality on homogeneous spaces. One passes from the orbits of gamma on G mod H to the action of H on G mod gamma. And in the second case, one would use the ergodic theorems for SL2 in order to deduce this result. Okay, thank you very much for your attention. Well, I mean, you can get some result, but I'm not sure about the accuracy of this estimate. Yeah. The norms don't. It doesn't really matter in this case. Yeah, no, it doesn't really matter. Sorry. The three torus, there is a result, but it's not optimal.